So, hello you beautiful people. I'm a little bit late for the new lecture, sorry about that. Today we will have a look at the full synthesis loop for the ammonia production process. Okay, so today we will have a look at the process layout with some temperatures, mole flows, composition and so on. And then I want to show you how you can simulate it with DWSIM. And it was the reason why it took me quite a while to get good initial values and to show you a procedure that hopefully works fine also for you. So I had this, of course I had this solution, but I wanted to show you a method how to securely get a valid result. And then, of course, some homework, but this shouldn't be too much work, basically. If you watch this lecture, then it should be possible to do the homework. Okay, let's start. So, some parts you already know. We start here with the reformer gas, 45 degrees Celsius, 30 bars, and then we have a compression in four stages, and we want to do it in such a way that at the outlet of stage 3 we have 280 bars. And yes, so no matter what's the outlet pressure of DWSIM, we want to have 280 bars here for the inlet to the fourth stage. Okay, so here we mix it with the recycle flow, and then we send it to the condensing of the ammonia cooling or ammonia condenser, and before that we have some internal heat exchanger. So this means we start here with 35 degrees Celsius, then we cool it down to nearly 24 degrees Celsius, then we have the ammonia, we condensate it at a temperature of 3 degrees Celsius, but we won't do this with a gas-liquid separator, but instead we will use here a compound separator where we just say, okay, I want to remove 10.5 tons per hour of ammonia. And this also means that we have 3 degrees Celsius here. For the gas flow, then we have internal heat exchange and we heat it up to 15 degrees Celsius. Then we split up our mole flow. We preheat it to 150 degrees Celsius. Then we have another internal heat exchange, 400 degrees Celsius. Then we have the feed injection in between. So we did this in the last simulation, and this you should know. And then it leaves the reactor with a temperature of, or it leaves the heat exchanger with a temperature of 300 degrees Celsius. So with this off gas from the reactor and 300 degrees Celsius, we produce steam. So let's say, okay, we start with liquid water, 25 degrees Celsius, 50 bar, and we want to produce saturated steam. So this means a vapor fraction of approximately 1. And yeah, so you know water, and then you know the mass flow here, you know the outlet temperature 175 degrees Celsius. This means that you can calculate your mass flow of water or of steam that is produced here. Okay, then this is sent to the first heat exchanger. It's cooled down. In the literature source I found a temperature of 86 degrees Celsius, and then it's sent to the condenser. Here you do the condensing with cooling water, let's say 20 degrees Celsius as an inlet temperature maybe, and yeah, then it's 30 at the outlet, 30 for the ammonia. Here again we use the compound separator and not the gas-liquid separator. Then you purge. Here you have a mole flow of 225.3 kilomoles per hour, and the rest is sent to the fourth compression stage. Okay, so compared to last lecture, now I gave you some more temperatures. We know, so here this should be 300 bars. Outlet of the fourth compression stage should be 300 bars. Okay. So here I gave you some more temperatures, I gave you some mass flows. so you know the amount of ammonia taken from the cooling water condenser and from the ammonia condenser. But as I showed you here, I put in some more figures. So for this, I also give you the outlet composition at the reactor outlet, and I gave you 0.4 after the condenser and after mixing with the reformer gas, and I also gave you the composition of the reformer gas. Okay, so here you have all the values, and what is your task now? You should try to create a simulation where you get some values that are close to these values here. Okay, but what's special here? So in normal life, you don't know the compositions and the flows. You do not know in advance. So they are not known in advance. And I think for your first project, you will get a task that is quite similar. This means you don't know all the values, but you just know the inlet values and the reactor design, and yeah, then you have to get all these values. So all these values that I put with a gray background, you do not know in advance. You only know what's going to the process and what's leaving the process. And to achieve these results, you have to somehow have good initial values. Okay, I forgot this. This is important for slide 6, I think. If you look here, then you see, okay, there's we have two inert components. We have methane and argon. And if you look here, they have a factor of 4.4 between methane and argon, and we will use this afterwards. Since both components are inert, normally the ratio between should stay almost constant, so it should be something in the range of 4. And we will use it afterwards. Okay. Something that's a little bit special is the condenser here. It's also valid for this one, but here I found more data in the literature source. Herefore, I found, okay, the liquid ammonia that is removed from the process is not pure ammonia, but so it's only 97% pure ammonia, and the rest is hydrogen, nitrogen, CH4 and argon, and so on. And yeah, somehow you have to implement it in DWSIM. And the way I did it was to first say, okay, let's cool it down to 30 degrees Celsius. This is done by cooling water with the inlet temperature of 20 or 25 degrees Celsius. I think it was given here. It's cooling water with 20 degrees Celsius. It's also written there. And then you don't have a gas-liquid separator, but you have a compound separator. So the gas-liquid separator is not working for the values here. So in real life you would have something like a condenser efficiency. This means that not all very small ammonia droplets that are formed cannot be removed from the system. And the other thing is that you have a solubility of your gases in ammonia. And if you want to do this, then you can implement a compound separator. And what I did for my simulation is that I specified the mass flows. And this means, okay, you know, I want to remove in total 27.6 tons per hour. And it should be mainly ammonia. Then you can say, okay, let's play around with the mass flow of ammonia, and then with the mass flow of hydrogen, and so on. And then you should end up with a composition of your ammonia removal here, the ammonia taken from the process, that is somewhere in the range like this. So maybe you could also calculate it, but I was too lazy for it. I played around with the figures and I specified the mass flows. Okay, this is well, this is how I implemented it in my simulation, and I would recommend it to do it also. Okay, and now is the question how to get the initial values. If we want to do this, then we can say, okay, what do we know about the process? We know that we have the reformer gas, we know the composition, it's given in the table, we know the inlet temperature, we know the inlet pressure. And what do we know? We know that we remove, by this cooling water, we remove 27.6 tons per hour, and in the second stage we remove pure ammonia. This is 10.5 tons per hour, and we also have the purge. And for the purge, we have a mole flow of 222.3 kilomoles per hour. Okay, this is what we know, and we can use this somehow to do a little balance for our methane. So what do we know? We know the mole flow here, and we know the composition. So we can say, okay, our methane coming to the system should be in the range of 52 kilomoles per hour. Okay, then we can calculate the mole flow of the ammonia. We know the content of methane that is leaving the system together with ammonia. Then we will end up with a value of roughly 18 kilomoles per hour. So here we have just pure ammonia, so no methane is removed. And this means if we know, okay, we put in 52 kilomoles per hour and we remove something like 18 kilomoles per hour here, then the difference has to leave the system by purging. If we would purge less than the two here, then the CH4 amount would increase. Okay, so what's this? Is this of any use? Yes, it is, because now we can say, okay, I know that I have to purge, or I want to purge 222 kilomoles per hour, and I know the mole flow of CH4 that I have to purge. Then I can calculate the methane mole fraction in my purge flow. So this is just the mole flow here divided by the total mole flow, so it's 15.3%. And then we can use, okay, so we will have something like a ratio of 4.4 of argon, of methane to argon. So if we just divide this mole fraction here by 4.4, this means we should have something like an argon mole fraction of 3.5%. Okay, this we know already. Then the next thing is, if we look at our ammonia condenser, then we can say, okay, it's coming here from the reactor. After the heat exchangers, we have a mole flow n dot here. We are removing some ammonia here, and yeah, we know the mole flow that of ammonia. This is the mass flow divided by the, or this is approximately the mole flow divided by the molar weight, and then we have a purity of 97%, so we can calculate, okay, the ammonia that's leaving the system is something in the range of 1575 kilomoles per hour. Then we need some assumptions. We already calculated this reactor, so we know a little bit about it. So maybe let's say, okay, the mole flow here coming from the reactor might have a mole fraction of 17%. And the next assumption is that after the cooling with cooling water, after the condensing with cooling water, we might have a mole fraction of 8%. So this is an assumption. Hopefully it's quite reasonable. And then we can do our mole balance. Then we can say, okay, the mole flow here times 17%. This is the ammonia going to the condenser, and this should be the same as the ammonia that is still in the recycle loop. So this should be the mole flow minus the reduced minus the ammonia leaving the system. So our mole flow here is reduced times 8% mole fraction, and then we also have to take into account that the ammonia here is leaving the system. Then we can rearrange it, and then we say, okay, our mole flow at the inlet of our condenser or at the outlet of our reactor should be in the range of 16,100 kilomoles per hour. Okay, so now we know the purge composition here, and we know the mole flow here, and we also have an assumption for the ammonia fraction, and this we can combine. So for our simulation we need a specification, or we need the initial values for the outlet stream of the reactor. So this is the mole flow 3. So what do we know? We can say the mole flow should be in the range of 16,100 kilomoles per hour. Then we know, or let's assume 17% of ammonia at the outlet, and then we calculated the mole fractions for our purge flow. So there we had 15.3 and where is it? 15.3 and 3.5. So since we are just talking about initial values, we don't need the exact values, we just need a reasonable guess for this value. So we say, okay, the mole flow is a little bit increasing if you go from 4 to 3. So this means your mole fraction of methane and argon should be a little bit lower. So let's say 15 and 3.4. And then we can sum it up and say, okay, 35.4% is occupied by ammonia, methane and argon. And this means the rest should be hydrogen and nitrogen. So 64.6% should be hydrogen and nitrogen, and we know that for ammonia production we need a ratio of 3 to 1. So we just have to divide 64.6 by 4. This is 16.15. And 3 times 16 is this 84.45%. So with this, we have our initial values for our simulation. So now we somehow got reasonable values for our mole flow 3, and this we can implement. And where do we implement? So this is outflow of the reactor, and we just do it after the steam generation. So we cut our process here. Here we should, in a later stage, we will have a recycle block here, but right now we are not simulating a full loop, but we are leaving the process open in this position, and we are just saying, okay, we have the mole flow here of 16,100, we have the composition from the previous slide, we have a temperature of 175 degrees Celsius, and then we try to initialize our simulation. Okay, this means you have to create the process simulation for the full ammonia process. This means you have to implement all the heat exchangers, you need the 2 compound separators, you need the compressors, etc. And what might be helpful to you is that you can use copy and paste. So in one lecture we had the compression system, and in the other we had the detailed model of the reactor with the 3 plug flow reactors, and you can just copy and paste it from one file to the other. So I tried it, it worked for me, so you can do it all the same. Okay, and if you do it, then you have afterwards you have to implement the heat exchangers. But what's important, do not close the loop for the reactor. This means no recycle block at the outlet of the steam generator. And then I find it helpful to stop the solve mode. This means you have here something like a power button, and if you press this, then the simulation is not starting with the iteration, but you can change all values until you are happy. So with this, you can implement the initial values and solve the simulation. And only after you have implemented the initial values, solved the simulation and saved it, then you can insert the recycle block in the right position. Okay. After this I will go to DWSIM, but what I want to show you beforehand is that here you can see my system of the 3 plug flow reactors. Here you have the recycle that's coming back, then you have the split up for the intermediate injection, then you have the internal heat exchange, you have the steam generator here, and here my loop is not closed. So normally if you have the loop fully closed, then you would have a recycle block here in this position, and then it's sent to the cooling to the cooling water, then you have the compound separator, then you have the purge, and so on. And as you can already see here, you have a lot of recycle blocks, since we have the splitter and we have the recycle to the internal heat exchange and so on. And to get reasonable results, I would recommend you to set the tolerance for all recycle blocks to 0.01 bars, 0.2 degrees Celsius and 10 kilograms per hour. And if you do this, then it still takes really a long time to get convergence. So I think it was, on my computer it was like 10 minutes. And also in between I got the notification that the solver wasn't able to find a solution. Then you just have to say, okay, solve it again, and then hopefully after a while you should come up with a reasonable solution. Okay, so here, this is my material stream 15, and here I just entered the value that we had here on the last slide. So these values I put in here, and these are the starting values for my simulation. And then if I say with this, if I say, okay, this is my initial value, then the whole reactor loop and so on is simulated based on the study. And then hopefully I will get some values here that are not so far off from our starting values. And then afterwards I can start the closed loop simulation. Okay, let's go to DWSIM so that I can show it to you there. Here's the DWSIM model. Here's my plug flow reactor. Here's my compression system with the 3 stages. Then you have a mixer. Then it's the 4th stage. Then I have the internal heat exchange. Then I have the cooling with liquid ammonia. And then I have here the compound separator. And here you just specify, okay, you want to have a mass flow of ammonia. Okay, I didn't do it here with the mass flow, sorry about that. Whoops. What's wrong here? Okay. Found a small mistake in my simulation. Well done. Okay, I will take care of it by hopefully this should work nevertheless. Okay, and what you have to do is for every recycle block you have to make sure that these tolerances are correct. So it should be 10, 0.2 and 0.01. If you would leave it with the initial values, then it might take you too long to get convergence. If you have a too big tolerance, then you might get wrong results. Okay, so here's my material stream where we want to start, 16,100. Here's the composition, as I already told you. And if we have it like this, then we can say, okay, solve simulation. Then I always don't get confused here in the splitter for the purging. I always get an error message, but it should be of no importance. For the splitter, I just said, okay, I want to have for my flow 1, this should be the amount of 222. For flow 2, I just set 0, and then all the rest is sent to material stream 4, to material stream 3 or outlet stream 3. And this means, so if you don't specify, or if you don't insert the second one, then it's not that easy to get the right purge rate. Okay, if I have it like this, then I switch off my what is it? My automatic solving of the flow sheet. Then I said, okay, I have to insert a recycle block. Then I have to change it. So 10 kilograms per hour, temperature tolerance should be something like 0.2. And here, so if you would have a pressure tolerance of, so this is 0.1 Pascal. And if we are operating a high pressure system with 300 bars, then it's not that important that you have a pressure accuracy of less than 1 Pascal. So here we can just say 0.01. Okay, then make sure that you press enter all the time, and then you can connect it. Oops, 15. Okay, so then you should solve it. And after solving, then you should save it, and then you can try to solve it. Okay, I'm not doing it because this will take like 10 minutes, and I don't want to show this to you in the video. Okay, so basically what you have to do, you have a model for the reactor already, you have a model for the compression system, you have to combine them, and you have to insert a lot of heat exchangers and so on, the compound separators, the splitters for the purge, the mixers and so on. But once you've done this, then you can start with the initializing the system, and after that you can implement the recycle block here, and hopefully you will get convergence. Yes, okay, I think this will be quite a long video, sorry about that. So for your homework, everyone must do the simulation, then afterwards you have to discuss it in your group. I think you're a little experienced with it, and then each group must hand in a PDF. You know this, you have to hand it with in the email room, and for this PDF you just should do a comparison of the material streams 3, 4 and 5 with your DWSIM results, and you have to compare it with the values given on slide 4. So, and you have to compare it with temperature, mole flow, component amounts and or composition and so on. And I can already tell you that you won't have 100% agreement, and you should give some reason for possible deviations. Okay, so basically that's it. Just as a short additional information. Some of you heard the master's course Chemical Reaction Engineering, CRE, in last semester, and there all the corona crisis began, and I showed you how to do a simulation for the corona model as an autocatalytic reaction. And so in summer times there was not so much corona going on. That's why I didn't have a look at the corona simulation, but right now it's still increasing, and that's why I updated my simulation. And yeah, what you can see here you have the daily new corona cases. The blue line is a simulation, and the circles are the cases of the Robert Koch Institute. And you can see here, so this is a simulation that I created on the 30th of October. So this was, I think, the Saturday before the lockdown was taking place. And you can see here that from the simulation point of view, you would normally have a much higher rate, then it should go down and then decrease. And the values right now are, so from my perspective, they are quite okay. So you can see that it's quite similar to what I simulated in spring this time. So hopefully the values will stay on this level for the next day and then afterwards go down, so that we might see something like 10,000 new infections per day or 5,000 new infections per day, that we might have this by end of the year. Okay, but yeah, I'm also curious to see how this will evolve in the future. Okay, this just if you're interested in this, then there's also a playlist on chemical reaction engineering on the YouTube channel, and then you can just have a look there how you can simulate it. Okay, so thanks for watching and good luck with the homework.